move forward. We have done the common source amplifier. Today we will talk about common source with degeneration. Let's compare these two circuits, except the drawing are not the same. Can you spot what's the difference between these two circuits? There's a source resistance. Very good. So it is still common source. Right? I did not say clearly this is V in and this is V out. Input is still at the gate. Output is still at the drain. The source is still common to each other because I don't have any signal. Right? In principle, this will change actually. But because it's derived from common source, so we call this common source with degeneration. By inserting a so-called degeneration resistor to it, which is RS. Right? Why do we want to do that? We will study. But let's first of all, you have a new circuit. You want to understand from an intuitive point of view. Okay? Like what we did for common source. Common source, right? So, when you get a new equipment, you will try to turn the knob, that is the input, and try to look at the output, right? That's very natural. Now I give you a new gauge. You want to play with that. So the first thing, as I told you already, this is common source, and you look, and this is gate, this is drain, this is source, and this is input, V in, right? So naturally, I want to put something to the V in to see what happened to V out, right? But here we use the so-called gate mental exercise or Gate-Duncan experiment, whatever you call it. We don't have the transistor in front of us, right? So let's say, okay, I want to increase V in by delta V. I just increase V in, right? In this case, it increased delta V. Then you want to see what happened to the transistor. But in all transistor equation, right, it is delta VGS, right? So what happened to delta VGS when you increase delta, V in by delta V? I think you will increase by delta V. Just a short-sighted thinking, right? I increase VG, right, by delta V. So in that case, what happened to the ID? If I increase VGS by delta V, increase also, right? Because again, IDS proportional to VGS minus VT squared, which we spent a lot of time to study before, right? Good, so increase. Then how is it going to affect the V out? Well, if IDS increase, V out is going to decrease, because V out equals to VDD minus RD times ID, right? So you increase ID, of course this will decrease. You should already have this feeling, right? Whenever you see common source, the left go up, the right must go down. They go in the opposite direction, right? That is okay. Looks like we finished. Isn't that this is the same as common source? That is what we discussed in common source, right? But however, we forgot about this. When IDS increase, at the same time, what happened to VS? This is IDS, and this is grounded. What happened to VS? And more current going down, what happened to VS? VS increases, right? Just Ohm's law, right? Because VS equal to 0 plus IDS times RS. It's going to increase. Then what does it mean? Very good. VGS will decrease, right? So now let's look at this. One of them say VGS is going to increase. One of them say VGS is going to decrease. Contradicting each other because we are not really solving a self-consistent equation. We're just showing the trend. These are the trend. When I increase VGS, I do try to increase when I increase VG, I did try to increase VGS, right? But at the same time, Vs also try to follow me. This is just the physics. Because when I increase Vg, I have more ID, and then Vs will go up. So basically, I have these two trends, 1 and 2. It just tells us that VGS increases VGS increases less than expected or less than common source. Right? So we go through this, we actually have a good feeling about this circuit already. It works like a common source, input increase, output decrease in absolute value, but it decrease less than common source because of this degeneration resistor. It try to push up the Vs. As a result, my effort is reduced. I increase Vin by 10 millivolt. Turn out that VGS only increased by 5 millivolt because the Vs also goes up. Is that clear? Any questions? Yeah. So why we want to have a circuit like this, right? We'll discuss more later. But in summary, you see that, right? It has a smaller gain, right? Right? It has a smaller gain because I increase my Vin by 10 millivolt. In the common source, my Vout may reduce by, let's say, 20 millivolt. But now when I increase Vin by 10 millivolts, my output may only reduce by 50 millivolt because the effective VGS did not increase by 10 millivolt. It only increased maybe by 7.5 millivolt because the Vs comes up. Is this okay? Let me give you some numerical example, right? For example, this can be 10 millivolt. Then I extend, I hope that this will go up 10 millivolt. But then, because, okay. But then it turned out this increased by, let's say, 2.5 millivolt, right? So overall, this one is only 7.5, right? 10, but this increased by 2.5. So overall, you only increase by 7.5. Okay. So, but what is the advantage of this one? The advantage is that this is the so-called, this is a negative feedback. You probably already can feel it. The resistor is doing something in the opposite direction I want to go. I want to make the output really low by increasing the input. But resistor stop me from going too low. It's just a negative feedback. Okay? And this negative feedback has a lots of good property. It increased the linearity. It reduced the sensitivity to loading, right? So let's do not talk about this here. We will talk about feedback at the end of the class. It has all the good property of negative feedback circuit. Okay, increase linearity, reduce sensitivity to the loading, to the process variation, or etc. It has a good control. Okay, so it's not a purpose here, so we'll just only talk about this. Okay, so we have the intuition, right? You know this very well. Now, then, our goal is to do it rigorously. Because once we do it rigorously, we know that we can use it in other more complicated circuits. So on the left, again, this is the common source amplifier with degeneration. We have the gate here. We have the drain here, the source because it's NMOS. So we start drawing the small signal. This is the gate. This is the drain. This is source. Because I say there's no channel length modulation, so I did not draw the R0. And then outside of it, I connect the gate to the input. I connect the drain to RD and then to ground. Why it is ground? Isn't that is VDD? I have not decided what to measure yet. I have not decided whether it's measuring out, in, out, or gain. So I cannot do any definition yet, right? But I'm still correct to connect this to ground. Why is that? Isn't that is VDD? Because it is DC. We're doing small signal. That is very important, right? I know this is trivial, but we need to remind ourselves all the time. So because it is DC, right? Good. So we drew the circuit, then the rest is just to solve the equation, right? So my goal is to find out what the gain is. So how do we do that? Well, there are not many choices. Just do KCL, right? So the current going through the RD is what? I RD must be equals to GM V1. What is IRD? What's IRD? How do you find it? Ohm's law. Look at the direction. How did I draw it? Thank you. 0 minus V out over RD equals to GM. What is V1? Now this is I even did not notice this is drew oppositely, but negative Vm. Like this, you just treat me as tricking you. I also trick myself. I did not realize this in my cheat sheet. Okay, so let's follow this figure. V1 is V1 is V1, but is it negative V in? We cannot say that. What is V1? How do you define V1? I'm sorry. First of all, this drawing is completely wrong. I cannot do, because I already say GMV1, so this drawing is wrong. I need to fix this. This needs to plus minus, because if I say current going down, then it's saying that when VG is larger than VS, I have current going down, right? So this is the small signal model. I should not mess up. This is a wrong drawing, okay? So let's do it again. What is V1? VG minus VS. Very important. Okay? Do not just say V in. Because now this time is not that simple. It is what? So I have negative V out dy RD equals to GM times V in minus what? Whatever, VS, whatever you call it, VS, right? Because this is not zero. That's why you cannot say V1 equal to V in. If you do that, wrong, okay? So from now on, be very careful when you put in the voltage. Do not just take one point, because all voltage are potential difference, okay? So we get one equation. Not good enough because, yes, I have V out. I want to find a gain, but I don't know what is VS. Well, just set up another equation, right? Second equation, I can relate GM to this one, or I can say this current actually is the same as this current, right? It's all the same. So it's up to you how to do it. But I decided to use IRD also equals to IRS. Is this okay? Yeah, although they are not next to each other, but they are equal to each other, right? So IRD again is negative V0 divided by RD, but what is IRS? VS, yeah, minus 0 divided by RS, right? Not negative because of the way I draw it. Yeah, maybe this arrow is not sharp enough. So then what do we get? Vs equals to negative V out divided by RD times Rs. Okay, so good. I have this equation and this equation, right? I just combine them. I call this is 3. This is 4, right? So 3 and 4 is going to give me, I just plug in, right? Just math. On the left, V out divided by RD equals to, on the right, GM V in minus Vs, but minus Vs is plus V out divided by RD times Rs. Right? I just plug in Vs to here. Is that okay? Just plug in. Right? It's just solve equation. This is nothing electrical engineering. Right? So I want to multiply RD. I have negative V out equal to GM RD V in, right? Plus GM Rs V out, right? Because I just put RD to here, so GM RD, right? Then take the whole thing into it, GM RD V in, and then GM RD times whole term, RD got cancelled, so GM Rs V out. And a good way to check is this is voltage. This is voltage, and GMRD is uniless. GMRS is uniless. So I'm pretty confident I'm probably right, just by checking the unit. If you miss one of them, you need to know that you are wrong, right? Group the term, V out divided by V in. I just need to make take this whole thing to the left, right? And then on the right is GM RD divided by 1 plus GM Rs. Right, and then check my cheat sheet, which is correct or wrong. I missed one thing. I have a mistake here. Okay, do you see what mistake I make? Thank you. Very good. Negative. I forgot the negative. Yeah? And it makes sense because it needs to be the negative gain, right? Isn't that we just say that V in goes up, V out goes down? So the gain needs to be negative, just like common source, right? That's another way for me to check that if I'm doing it right or wrong, right? Compared to this, right? So yeah, we've done this, but so what? The point is we want to see if it makes sense with what we have learned. What's the difference between common source and common source with degeneration? It is this resistor, right? If the resistor equal to 0, what should that be? Then it should become a common source. Then let's check the equation. Indeed, the gain becomes negative GM RD divided by 1 plus 0, which is negative GM RD. Is it the same as the common source we derived? Yes, it is, right? So if in the future, right, exam or when you are working, or not just this field, you come up with something new, look at the extreme case. Morph it so that it becomes something you already learned, and compare if you get the same result. If you don't, then probably you make some mistake, right? If you do, there's a high chance that you're right. You might still make mistake, right? So there's one common source. Another way, this is just for checking, but another way for learning is that then you might think, what if I make Rs very large, right? If I make RSGM very large, what happened to the gain? V0 divided by V in, you have a very large GMRD, GMRS, right? Because this is much larger than 1, then I can ignore 1, right? Because this may be 1,000, for example. Then I can ignore 1. This becomes negative RD divided by Rs. The gain does not depend on the transistor anymore. And that is why I told you earlier, it's less sensitive to variation. Transistor, you might have a lot of variation. Now, whether you are using a transistor from TI or a transistor from, I don't know, IBM or whatever, analog device, By using this circuit, if you have large enough GMRS, you get the same gain. And you are the one who put in RD and RS, or your customer can choose their RD and RS. They have a very good control. So if you design this circuit, you can have different vendors without problem because you get very similar gain, right? But if you use common source, you really depend on GM. Then you need to talk to, you can probably have only one supplier for the purpose that you want to have, right? So it becomes independence of GM. Or I would just say depends on RSRD only. It's difficult to see. Yeah, depends on these two only. Independence of the transistor. Okay, any question? How about the output impedance of this circuit, right? For as we said before, we do the DC biasing and then we extract GM and R out. You know all this already. And then for each circuit, you look for all the circuit characteristic, input impedance, gain, output impedance, and later even transit bandwidth, etc. How about the output impedance? Now, in this case, I cannot ignore the channel length modulation. Otherwise, it will be infinite, right? So now I want to look at the output impedance. So what should I do? Again, this drawing has problem. This should be plus. This should be minus. Okay. So what is the definition of the output impedance again? Okay, Vx over Ix when V in is 0. I hope you can memorize this. So because of this, I ground the gate. Okay, I did not ground it here. It's V in. Now I can ground it because I'm looking at the output impedance. Just because I'm looking at the output impedance, right? Then I apply a test source to the drain, right? And I want to look at output impedance only to the transistor, not to the resistor. I just want to look at the output impedance due to this transistor. Then what do I do? I can just go through KCL and KVL. My goal is to find out what is the relationship between Vx and Ix, okay? So what is the relationship? Well, definitely the first is that Ix must be equals to the current going through out, right? Out plus GM V1. Yeah, that's what you said. Thank you. Why? Is it 0? Yeah. So let's do it one by one. What is IR1? It is Vx. What's IR1? Need to be very careful. Ohm's law. Which Ohm's law to use? Vx just Vx over R out? Vx minus Vs, or here I call it Vp. Yeah, Vp. Now this is, if you miss this again, the whole solution is wrong, right? And you see this is just Ohm's law. And we can do it, it's just because we are careless. Because we always think that just take one terminal, I know the current. It must be the difference of the... Can you say again? R0. Sorry. Just the right thing. Yeah, look like V, right? R0. Okay. Okay, good. Now, GM, what is V1? Why is negative VB? Can you just say the two terminal? Very good, very good. Because he was very careful. He just followed the rule. Plus, minus, negative. And then plus is VG. VP is VS. VG minus VS. This is the definition. It's drawn to you already. It's what you define in your cheat sheet, the model. We agree already, we prove already this is the correct model. So it must Vg minus Vs. So this is 0 minus Vp. Okay, do not just say 0 or do not just say Vp. It's 0 minus Vp. Okay. So with this, then I get Ix equals to Vx minus Vp divided by R0 minus Gm Vp. Right, so it's pretty messy. Let me just group the Vp together. Vx divided by R0 minus Vp times 1 over R0 plus Gm. You might see something. Some of you might already see something. Gm is the conductance. 1 over R0 is the conductance of R0 also. Two conductance adding together is two parallel conductance. So this is just 1 over the parallel resistance of R0 and Gm. But I don't want to go to this detail. This is just 1 over R0 parallel 1 over Gm. You can go over the math. But another way to see it is just like what I said. Conductance plus conductance means that they're in parallel, right? Then, if I treat it as a resistance, then it's just a resistance, parallel resistance, and take 1 over. This is what you have, right? Or you can go through the math, right? But this is not important here. I just put here, right? So I still don't know what is Vp, right? This is one equation. So what is Vp? Do another equation, right? How will you do it? I have Ix going here. So what should I equate? Ix equal to? Say again. IRS. What is that? How do you find it? Thank you. Vp minus 0. I'm waiting for this type of very simple thing, right? High school or even middle school question, right? But this is important. Otherwise, you will mess up. Even now, this time turn out that you just say Vp is okay, right? So with this, then we say that Vp equals to Rs Ix, right? Vp equal to Rs times Ix. Now, some of you might already realize this. You don't need to write this equation. You can just plug it if you already realize that, right? So this is messy. So from 1 and 2, then I will get Ix equals to Vx divided by R0. And I have Vp minus Rs Ix, right? And then the whole thing, I will just do this, plus Gm. Okay? And eventually, I did not plan this well. This is pretty lengthy. Eventually, I need to do Vx divided by Ix. Okay? So I group the term. I do Vx divided by Ix. Then I have R0 on the right? And then divided by 1 plus Rs. Did I do something wrong? Times 1 over R0 plus Gm. I think did I do something wrong here? This is current. This is current. Vx divided by Ix. Let this go up. Yeah, I'm wrong about this, right? So this should be multiplication. Do you see this? This is plus Rs times 1 over 0 plus Gm. Do you see this? What mistake I make, right? So this is Vx divided by R0, and I put this to the left. Then I have Ix, which is 1 times 1 plus Rs times this whole term, right? So I just keep this 1 plus Rs times whole term, right? And then just multiply by R0. Then I get this. Okay? So what do I get? So bad. Let me go here. This is what I get. R out equals to R0 plus Rs plus GM Rs R0. Okay? Or I can do this in this way. It is equal to, I'm going to group the first and the second term. It is actually the same. I can group the second and the third term. It's R0 1 plus GM Rs plus Rs. Now, this is a lengthy equation I want you to memorize. But more importantly, I want you to see this. Because GMRS is much larger than 1. This one is approximately equal to GMR0. R0 times GMRS. Do you see that? Because this is much larger than 1, so I can ignore this 1. Then I have R0 GMRS. But R0 also much larger than 1, then I can ignore this Rs also. So eventually I have R0 times GMRS. But why do I want to do this? Isn't this is great already? Yeah, this is great. You need to memorize this equation. But why I want to do this? So then I can correlate to what? To the common source amplifier's output impedance. What was the common source amplifier output impedance? Do you remember? Forgot? We just say it. What's the common source output impedance? Just R0, right? Due to the resistor, right? Of course, you've had RD parallel. But now what is this? R0 times GMRS. Is it large or small? You have R0 times something, yeah. Of course, you say, I don't know what is GM, maybe 0.001. But usually we make this term larger than 1, maybe 10. So the output impedance is much larger when you have source degeneration. Okay, so that is the main reason we want, one of the important reasons, another important reason we want to use source degeneration. It has a much larger output impedance. Yes. Now, so he said that, isn't that we keep saying that we want ideal voltage amplifier to have a low output impedance. That is true when you're driving the next stage. But however, in that case, you have very low gain. Okay, so now we want to make it high, so we have high gain. But to solve your problem, later you will see that we need to cascade it with another stage, which is source follower, which does not change its gain, but it reduces the output impedance. Yeah, so that is a trade-off. Very good point. Okay, you're trying to answer? Okay, good. Is this okay? Now, I know the math is a little bit messy, right? I want you to be able to follow. And then this is just do it yourself, right? I confuse you a little bit. But the point is, at the end, how you set up the circuit. The rest, just let Mathematica to do it, right? Or let your report to do it, right? When you're a manager. No, unfortunately. The most important is the insight. Now, you see that the reason I add this is I boost up the output impedance by GM times Rs. Okay? So now I want to study another concept, which is called the transconductance, which we did not study before. Got messed up. Okay, should be here. The transconductance of a common source amplifier. So first of all, what is the transconductance? We already know the transconductance of the transistor, right? What is that again? First, what is conductance? Just keep asking yourself, what is conductance? Very quick. What is that? Current over, 1 over resistance, which is current over voltage. Conductance, right? Transconductance. Why we call it trans again? Yeah, because it has different terminal. We're not talking about the same terminal. So what current over what voltage? Which current? I mean, what do you care about in a transistor? The gate current or what? The drain current, right? You cannot get it wrong. Drain current over what? Which gate? Huh? Gate voltage. It cannot be drain voltage. Otherwise, it won't be called transconductance. Right? Then you know it's drain current over gate voltage. Right? If it's drain current over the drain voltage, we call it output conductance. Right? Or drain conductance, whatever. Right? So transconductance is for a transistor, right? Is the drain current divided by the gate voltage. Same for a circuit, but now we don't have drain because it's very complicated. We will say this is just equals to the output current divided by the input voltage with the output shorter. That's it. And this is consistent with what we learned, because when we learn the transistor, that is also the transconductance, Vg, IDS. That is how we find the Gm equals to IDS divided by Vg, right? How much drain current you get when you change the gate voltage. This is, and that time we did not say this is just V in, and this is just I out. Because it just tells this is a very, very simple circuit, one transistor circuit. But now you can have a very complicated circuit, many transistors, many resistors, right? And it's still defined as a capital Gm, the transconductance, right? When I out divided by V in. Is that okay? So if that is the case, how should we solve that for a common source with degeneration? First thing, draw the small signal again. And I say there's no channel length modulation, I'm done. Plus V1, Gm, V1. Is that okay? You agree this is the small signal for NMOS? Then we start adding the input, V in. And then we need to hook up with the RS because this is a common source with degeneration, like here, right? Okay. How about the output? How should I hook it up? Based on the definition. When I want to find the transconductance. How should I connect the drain? Huh? We out to ground, right? And this is I out. And then the transconductance of this circuit is I out divided by V in when V out equal to 0. Same definition. Okay? Okay, so my goal is find the relationship between the I out and V in, right? What is KCL? I out equals to Gm V1. Agree? So what is V1 again? What is V1? V in minus Vs. Thank you. Let's call this S. right? So I still need to get rid of Vs, right? But I also have I out equals to IRS. What is that? Vs over Rs. Thank you. Vs minus 0, right? So with this, then I combine them 1 and 2. I have I out equal to Gm V in minus Vs, but you already told it from the second equation, this is I out Rs, right? So I group the term I out 1 plus Gm Rs equals to Gm V in. Is this okay? Gm V in and Gm Rs I put to here. Gm Rs 1 plus. So what is the transconductance of this circuit? Gm divided by 1 plus Gm Rs. What is the transconductance of a common source amplifier? We just say that it's Gm, right? Because common source amplifier is just that you don't have the Rs, so it's Gm. Which is correct. If I put Rs equals Cm, it is Gm. Compared to that, you see that what happened? Compare to common source, is reduced by 1 over 1 plus Gm Rs. Okay, so while the output impedance increased by about 1 plus Gm Rs, the transconductance reduced by 1 plus Gm Rs. And you will find out the gain does not change. So actually, we're not able to improve the gain at this moment. Okay, so in this slide, we learned two important things. One is the meaning of the transconductance of a circuit. This is the definition. Okay, so you put in your cheat sheet. And how do you do it? You ground the output and again solve KCL and KVL to relate I0 to V in. I out divided by V in. Is this okay? All right, so now let's start recollecting, right? We add something called degeneration resistor. We get the so-called common source with degeneration. We realize that it is the same as the common source, except that we have the degeneration resistor. It has negative gain by intuitive inspection. And we also expect the gain to be smaller because of the feedback coming from the source. We do show that the gain is smaller by 1 plus Gm Rs, right? The output impedance, however, is higher by 1 plus Gm Rs. But the transconductance, a new concept we just learned, or we just learned how to derive it, is reduced by 1 plus Gm Rs. Right? And this is when there's no channel length modulation. Now, so if this is the case, we have another gadget. Right now we are playing the game. We have another weapon now. I give you this circuit. Can you find the output impedance of this circuit? Right? If you look at this guy, the first thing you will think is, well, I know the output impedance of common source, R0. This is not common source. It has two transistors. Well, I also know the output impedance of common source with degeneration. Again, this is not common source with degeneration of the circuit we have just learned. This is the common source with degeneration, right? On the lower right. Yeah. So I do know what the equation is. This one, this is R out equals to, what is that? R0, 1 plus Gm Rs plus Rs, right? I can memorize it. Let's check if that's right. Yeah. R0 plus 1 plus Gm Rs plus Rs. I also know this guy. I know this equation, right? Then what should you ask yourself now? Very good. Can you model the transistor and resistor, or before this question, can you map this one to here, right? So then you start saying that maybe I can, first of all, R out again is V out divided by I out when is 0. This is a very critical point because you still very worry at the time because you say, this is V in, this is VB, this is not V in, right? But however, when I try to find the R out, I need to ground this guy. And I went through all those complicated math, I came up with this equation. But this is constant bias, isn't that? I need to ground it also because this is AC ground. I'm doing small signal, right? So this is AC ground. So I will also ground this guy, isn't that? Now, then I start mapping. Well, I try to look at R out, yeah. The gate is grounded, the same. Source is, drain is here, source here, drain is here, source here. They're exactly the same, except I'm given this extra thing, M2. And as you said, can I model this one as a resistor? If I can, then I can use this equation. Then your question is, what is the resistance when you look down? You can use soft small signal or check your gauge again. What do you learn already? Can tell you what is the resistance when you look down. Common source or just the drain resistance when the gate is grounded. We learned this already, right? And that's why we transform to this circuit. The whole thing is nothing but just this circuit, right? Now you compare, this part is exactly the same as this part. This part is exactly the same as this part. So, without doing any math, I now know that the R out equals to R01, 1 plus GM, 1 or 2. GM1. Because the GM here is the GM on top of the resistor. So this is GM1 times RS, which is R02 plus R02. Done. You can spend the whole day to solve this circuit. I only use it in a minute, right? So now you need to be able to do that. Okay? There was a midterm, I gave them 3 transistors instead, right? You can continue to keep going. Okay? Good, so that's very good. And now, just want to review one more time, right? When we are doing DC, we were doing, yeah, question? What I'm trying, okay, so since you asked, why don't we just play with this together? You need to then think about how you can map this circuit to this circuit, right? Then the first thing you say, I want to treat this whole thing as a resistor, RS, right? Then I can plug into this equation. But then what is this RS? This RS is not longer R02, right? But if you look down, what is this circuit?
Series.
It's just the same as this circuit. So your new RS dash is this whole thing. And then you plug in into that equation again, right? So in principle, it's just looping, like when you're doing programming, keep looping. I mean, substitute, call the same word function, self-call yourself. So you keep expanding the term. So we have been, we devoted some time to do the DC analysis. And then when we're doing small signal, we kind of remove the DC and I just say that, we bias it correctly. But how do you really make a circuit, right? If you really want to make an amplifier, you need to really bias it with all the small signal. So here I just want to remind you, how do you do that? First of all, I need to analyze it. For example, I can find out what is VG. VG is equal to VDD times R2 divided by R1 plus R2. This is just the potential divider, right? And some of you might feel why it is so simple. That is because the current is 0 here. The DC current is 0 here, right? So basically, you only have this column, right? That's how we bias it. And of course, then we also need to make sure that the V out, which is VD, which is VDD minus ID times RD, needs to be larger or equals to VGS what else? Minus VTH, so that it is in saturation. Very good, right? And then ID equals to W on L, mu C ox divided by 2, VGS minus VT squared. Yeah, maybe you even want to add the channel length modulation depending on the question you want to solve. This is the biasing. And then based on your currents, then I come up with GM, right? Or based on your VTH, for example, what is GM is W on L, mu C ox, VGS minus VT, right? Because I got the GM here. I got the VGS here. I know this is 2 volt, 2.1 volt. I plug in, then I know my GM. I get my R out, which is 1 over lambda ID. I know what is ID now after solving this equation, right? Then I know what is R out. With GM and R out, then what do I get? I get the Z in. Here the Z in is a little bit, let's do the Z in the last. I know what is the R out of this circuit, which is RD parallel my R out, right? I know the gain. This is a common source amplifier because the signal is here, coupled through the capacitor, which is short circuit in AC, so it appears at the gate. So whatever V in equals to VG, right? This is V in. This is VG. V in equals to VG. So this is, then you see that this is a common source amplifier, right? So the gain is what? Remember, what is the gain of a common source amplifier? No, I mean the final result in terms of GMR. Oh. Thank you. R0 parallel RD, right? How about the input impedance? We keep saying that it is infinite, it's infinity, right? But now is it infinity? When I come in, yeah, I see infinity here, but what else? You can go up and down. Thank you. You can go up and down. R1 parallel R2. So even at DC, you won't get infinity now because you need to bias the circuit. Okay? So in a real circuit, you won't get infinite input impedance. But that is the main point, the whole picture we have been doing now. Same in the future, right? Get a DC biasing, find the small signal value for the transistor, and then analyze the whole circuit. This is what you really get. Now, if you treat this as infinity, and then you try to calculate the impedance, you feel that you get a very good gain? No, because it's not infinity. You get some potential drop. You'll find that your amplifier does not work as good as what you want. Okay. So, what do I want to show here? Yeah, so he said, then let me set R1, R2 to be really high, then it's almost like infinity, right? And then the trade-off that is that you need to have a large resistor. And if it's integrated circuit, it occupies a lot of area. Yeah. And then, of course, it has noise. If you go to noise analysis, large resistor generates a lot of noise. So actually, I already solved this in the previous slide, right? Already discussed in the previous slide. Let me just rewrite it. Rin equal to R1 parallel R2. And then the gain is negative GM RD parallel R0. And then the output impedance is just the regular RD parallel R0. Okay. So let me see. What else do I have? I actually want to spend some time to go over with degeneration, and then we go back to the simulation if we have time. They're not very important. Now, this is the biasing of the common source with degeneration. You see that it's the same as before. We have this AC signal coupled through this capacitor. So whatever small signal, right? For example, this is 10 millivolt, and then this may be at 2 volt. Then you will have 2 plus 10 millivolts. Of course, this is AC, meaning it's fluctuating. And then you go to the transistor, right? But what is the gain of this circuit? Now, obviously, for the small signal, whatever put here, you will come here, right? Because we assume this is large, so it's AC short, right? VG equals to V in because AC short of C1. Okay, we just short it. So this is a common source with degeneration. So what is the gain? Probably you forgot already. It is GM RD divided by 1 plus GM. Very good. GM RS. But I call it RS dash. Now, because do I need to solve the small signal again? I don't have to. I just treat the whole thing as RS dash. Okay? But what is RS dash? Very good. 1 RS parallel SC2, right? So we need to work in the frequency domain to make it easy, right? So what is this? This is, as you just told me, RS divided by 1 plus SRSC2, right? Is that okay? Okay, so that's it, right? Now, but let's think about it. What happened at low frequency? At low frequency, 1 over SC2 is what? When the frequency is low. This is really large, right? Now in DC, it becomes infinity, right? So RS dash is approximately equal to RS. Because this is open circuit at low frequency, right? Even you don't need the math. At low frequency, this is open, right? So your gain is GM-RD divided by 1 plus GM-RS, okay? This is small because of common source with degeneration. The gain is small. Make sense? At low frequency. But how about at high frequency? What is 1 over SCS? Go to 0, it is small, right? It's just like you short the C2. Once you short the C2, what is RS dash? Just a straight line, 0. This becomes a what? Common source amplifier. I forgot the negative, I'm sorry. This is all the negative I'm missing. It becomes just a common source amplifier. To see that they bias in this way, then I can have a common source amplifier at the frequency I'm interested in. But then I have a low gain for the frequency I'm not interested in. This act like a high pass filter, right? Because all the low frequency parts has a low gain. For a high frequency part, it has a high gain. So this is a high pass filter, a common source with degeneration. Yeah. Oh, why I did not include R01? I can include it. Here, let's just assume there's no channel length modulation. Let me just say, yeah, I did not include it. Yeah, it just need the parallel. In this particular case, it just need the parallel RD. But here we assume no channel length modulation, but you can include. No, and another reason is because when I derived this question, this equation, I did not have the R0. Right? This equation only correct when there's no R0. Otherwise, it will be more complicated. But the result will be similar. Okay. Now, for common gates, let's do it next time. But let me show you the simulation.